Okay. Good morning, everybody, and welcome to day 5 of Climate Week at Penn. My name is Osek Eke. I'm the Director for Global and Local Service Learning Programs at Penn Engineering. Today, we have a fantastic program for you. Our topic is a case for removing carbon from the air, and we're lucky to have Professor Jennifer Wilcox and graduate student Noah McQueen, who will be introduced by our moderator, Mark Allen Hughes. Today's kind of a bittersweet day because it's the last day of Climate Week at Penn. And this week, we've had a program since Monday from Penn Engineering and other units around the school, around the university, trying to address the issue of climate change and also figure out ways to mitigate the effects of this phenomenon. So to help us navigate today's program, I'd like to introduce Professor Hughes. Professor Hughes is a professor of practice at the Weizmann School of Design here at the University of Pennsylvania. He's the founding faculty director of the Kleinman Center for Energy Policy. He's also the founding director of FEL's Policy Research Initiative in the School of Arts and Sciences. Professor Hughes is a distinguished professor. He's published articles in several journals. And of course, he's an environmentalist who is keen on this subject of climate change. Professor Hughes.
Osek, thank you. That was a very nice introduction. It's a real pleasure to be here. I almost feel like Climate Week at Penn is kind of a Ponzi scheme because we are constantly collaborating with each other and giving presentations across each other's centers and schools and everything else. It's fantastic. It's incredibly efficient. They leverage all of the great talent across the campus, and I'm so happy to be a small part of one piece of the amazing programming that SEAS has put on the table for Climate Week at Penn. It's really an exciting opportunity, and this is also my very first official public opportunity to introduce these new colleagues who have come to Penn as part of a major initiative by the president and provost to build a world-class energy policy faculty at Penn. Part of the idea behind that, building a world-class energy policy faculty, is to find the world's best scholars from a variety of disciplines that matter to the future of energy policy. And Jennifer Wilcox, the first presidential distinguished professor of chemical engineering and energy policy, is here today to present some of this work along with third-year doctoral student, one of her students that she brought with her from Worcester Polytechnic Institute, Noah McQueen. I just learned in the green room of this event that last year Noah was named the #1 TA across the entire university at WPA for the outstanding teaching that he has done. So I'm sure many of you are students out there and are now looking for the courses that Noah will be TAing perhaps next. So I'm going to turn it over to, I promised to be brief, I already haven't been. I'm going to turn it right over to Jen to talk about a very interesting, in terms of the science and technology, as well as the policy implications that she's been working on for a couple of years now. Take it away, Jen.
Great. Thank you so much, Mark, for that kind introduction. You can hear me okay? Great. So today we're going to do a little bit of a deep dive into some of the work that NOAA is doing, which is focused on direct air capture. But I'm going to introduce the topic by giving you a broader overview of what direct air capture is and why it's important in meeting our climate goals today. So negative emissions technologies, that's where I want to start. And what this plot is showing you is it's showing that we have a curve at the top that's yellow. That's the business as usual trajectory. And then the bottom curve is red. And that's the trajectory we need to follow in order to be below 2 degrees C warming by 2100. And what it also shows, if you look below the axis, the blue triangle is negative emissions. And I'm going to tell you a little bit about what negative emissions are, but the key here is that it's no longer enough to simply avoid emitting carbon into the atmosphere. Just avoiding carbon through increased energy efficiency, carbon capture at point sources, all of these kinds of technologies, switching to renewables, all of those things we need to do and at an increased scale than ever before. But even if we do all of that at the greatest scales we can, it's not going to be enough to meet climate goals because we've waited too long to do them at the scales we need to. And so now we're at a position where we need to start pulling carbon directly out of the atmosphere. And so what are the different approaches that can be used to do that? So it turns out, like, on average, globally, we emit about 40 gigatons of CO2 in the atmosphere. The ocean and the terrestrial biosphere uptake about half of that naturally every year. But since the start of the Industrial Revolution, roughly half of that has just been steadily accumulating in the atmosphere, such that we have gone from, say, 270 parts per million CO2 to up to 410 today. And it's been great that the natural systems have been uptaking a lot of our garbage that we've been dumping into the atmosphere, and it doesn't affect in a negative way the land sector so much, but we see the detrimental effects it has on the ocean with increased ocean acidification. And so when we look at the different approaches, some of them you can think of as nature-based. So what that means is, for instance, accelerating the natural sinks that already take place today. An example of that would be to plant trees, like afforestation and reforestation. Another example could be agricultural related, where you can do an increased storage of carbon in soils through low tillage or different agricultural practices. Another one is if we were to use biomass for energy resources. Biomass essentially is just taking CO2 out of the atmosphere, and if we can use that biomass as an energy resource and we couple it to carbon capture and storage, we're not allowing that carbon to be re-emitted in the atmosphere. So that's also considered a negative emissions technology. And then there's also rocks that are abundant in the Earth's crust, and they're rich with minerals like magnesium and calcium, and those readily react with CO2. But the problem is many of them are just locked in the Earth today. So we need to think of ways to take the alkalinity out of the Earth, react it with CO2 to try and enhance the uptake of CO2 from air. And then finally, there's the approach called direct air capture. And direct air capture is an approach where we actually use chemicals to react selectively with CO2 in the atmosphere. And we use these large air contactors that you see in this picture. The key is, though, is in order for that removal of CO2 from atmosphere to be permanent, which is what we want to meet climate goals, then you have to do something with it. And if we have to actually remove gigatons of CO2, that's a lot to do something with. And it turns out there aren't really sectors that scale to those emissions. We could imagine converting it to fuel, but when you burn the fuel, the CO2 ends up back in the atmosphere. So the primary method of actually permanently removing the CO2 is through geologic storage in the Earth, through different formations like sedimentary basins or even things like basalt. So a little bit more of what is direct air capture. So again, it's directly removing CO2 from the atmosphere, but one thing to mention is it's very, very difficult to do. If you look at the concentration of CO2 from a power plant, it's roughly 100 to 300 times more concentrated than the CO2 in the atmosphere. It's always going to be cheaper, and it's always going to be easier to simply avoid the carbon in the first place, avoid the carbon emissions. But again, we're not in a position where we can afford to do that anymore. The climate math is hard, and we need to do everything we can at this stage. And that includes things like direct air capture, even though they're more expensive than simply avoiding the CO2. But it should never be seen as a replacement for just mitigating CO2 in the first place. The plot that I'm showing here is a minimum work plot. So this is combining the first and second laws of thermodynamics. As Mark mentioned too, our backgrounds, both mine and Noah, were chemical engineers. And this is really some of the fundamental framework that we work in thinking about the problems that we try and solve. So if we were thinking about separating CO2 from a gas mixture, the minimum work is pretty much the limit of the energy, the lowest amount of energy would be required to do a given separation. And so chances are, that you're much higher than this because every process you choose is going to have some kind of inefficiency associated with it. And so what this is showing is that if you look at a more concentrated source, if you look at the x-axis, the CO2 concentration is increasing from left to right. And the more concentrated your CO2 is in a gas mixture, the lower the energy is to do the separation. And just roughly looking at, again, a point source like a power plant is three times less energy intensive than direct air capture. And if you look at, for instance, the size of the contactor, because again, the dilution in the atmosphere is 300 times less, that means that the air contactor has to be 300 times as great in order to capture the same amount of CO2. And so what this translates to is increased energy or operating costs and increased capital costs. So this is just a little bit of a background of what carbon capture looks like at a point source. And so this kind of design, what you see here, this is a Petra Nova plant. This is in Texas. It was capturing on the order of 1.4 million tons of CO2 per year. The CO2, the way that this was funded was primarily, was that the CO2 was being used to recover oil through enhanced oil recovery. And due to the low cost of oil and the prices dropping, this no longer became economical. Had nothing to do with the carbon capture not working. It's just that the utilization was no longer an opportunity for this project. And today, the way that the policies are for carbon capture, there's not a lot of incentive to actually put CO2 permanently back in the earth through dedicated storage. But the point in this is to show that when you capture CO2 from a point source, the way in which the scrubber looks, so I mean, just think about the scrubber when you purify water, like in a Brita filter. This is a very large scale for 1.4 million tons of CO2 per year, but it's basically a big scrubber. And so your gas is moving up and your liquid with the chemicals is moving down. And then ultimately in the end, you're cleaning the gas at the top of the tower. But when we look at a direct air capture contactor, it looks like this, huge surface areas. And so in order to capture 1 million tons of CO2 per year, and remember in that last slide is 1.4 million, you need 10 of these units. And so the design is quite unique compared to, or it's distinct compared to point source capture. You need that high contact area, and then you notice as you go into the depth of the screen, it's a very thin bed. And the reason for that is because you don't want to have to spend too much energy in terms of fan power to push your air through. So you have a thinner bed, which means you don't capture as much CO2, but you have to optimize because of costs. So what goes into these contactors? There's two leading technologies today that are really on the commercial edge of direct air capture. The top is a packing material that's called structured packing, and a company that uses liquid-based solvents is called Carbon Engineering out of Canada. And they're working on building the first plant that would remove 1 million tons of CO2 per year in Texas in 2023. The bottom looks a lot like the catalytic converter in your automobile, very different technology. It's a honeycomb structure with the chemistry is embedded in the walls of the honeycomb structure, and that would sit inside the contactor. The temperature differences are, the top one is about 900 degrees C, where the bottom you can use geothermal, you can use waste heat, it's about 100 degrees C. So very, very different technologies. So the work that NOAA's going to talk a little bit about is an approach that we call a hybrid approach. So we noticed that for the honeycomb structure or the solid sorbent-based technique for carbon capture, 80% of the capital cost is associated with sourcing the micro mesoporous materials, which have all of the surface area. 1 gram alone can actually have the surface area of a football field. But it's those materials that are very expensive to scale up today. In fact, they represent 80% of the capital. And so what we thought is, can we look at the Earth's crust and can we exploit some of the resources that are available there, either naturally available or even available as a mine waste from tailings? And can we use those to react with CO2 from the atmosphere such that the contactor becomes the land and the feedstock for reactivity is a natural mineral? And so to give you a little bit of an idea, well, where are all of these waste materials that may be reactive with CO2? And so in our work, we do a lot of mapping. And what we found is that when you look at tailings associated with gold mining, copper, nickel, and some of these materials will only become more and more increased in use with increasing batteries and catalysts. But it turns out that things like magnesium and calcium, which readily react with CO2, they're often correlated in the earth with these other minerals, oftentimes rare earth elements, and even things like diamond. And so the mining process, it's a lot of grinding. And so what they do is they get the rock, but they're really interested in these high value products. And so what they do is they are grinding down a lot of rock and leaving behind waste tailings. And those waste tailings can be as small as 50 microns, and they tend to be really reactive, especially if they contain lots of magnesium and calcium. So in our group, we're surveying all of these opportunities to look at those that are the most reactive. And then in the cases where you have some that are not, we're actually looking at enhancing their reactivity through different pressure and temperature conditions that we can control, again, kind of from a chemical engineering perspective. And then finally, you have to ask the question, well, where's the CO2 coming from? For the reactive stuff, we can actually use CO2 from air, and that's directly what Noah will talk about in the deep dive of his work. But in some of the other cases that aren't as reactive, another driving force that you can use is CO2 driving force. So if we look at, for instance, where is all the CO2 sourced, the bottom right is a rectangle with an inset, and what you see there is in the next 10 years, you know, all of the black and the blue that are outlined in red are going to be retired fossil power plants. So the black is coal and the blue is natural gas. But what we see is, you know, by 2030, most of the coal-fired power plants are going to reach their retirement age. And then we're going to be faced with this challenge of dealing with all of the decarbonization associated with the young gas fleet that exists today through mid-century. And so that CO2 sourced from that natural gas exhaust that's 100 times more concentrated than CO2 from air could be a great feedstock for reacting with some of the alkalinity. And you do that potentially through ex situ mineralization, it's what it's called. So you have these tailings, you might have to make them more reactive. And then ultimately you have to make a decision. Do we want to bring the rocks to the CO2 or bring the CO2 to the rocks? And that depends on if the infrastructure is available for pipeline transport or trucking transport of CO2. And then finally, just to mention, there are some policies associated with carbon capture today. The ones, there's a federal tax credit called 45Q. And so when you make, say, some of these rocks from CO2 and reacting them with available alkalinity, you can do different things with them. With those rocks, you could, you know, in Pennsylvania in particular, there's a lot of abandoned coal mines. You can use that to potentially try and remediate that land, but you can also use that as a feedstock for building materials, and that would be called utilization. If it's dedicated storage, a federal tax credit will give up to $50 per ton of CO2. If it's a utilization, it's about $35 per ton of CO2, it's maxed out. But there's also the low carbon fuel standard, and that's for the state of California. They have a goal to be fully carbon neutral by 2045. And they recognize that in order to be neutral, they need some carbon removal or negative emissions because of sectors like agriculture, industry like cement. In California, there's a lot of cement production, one steel plant, and the transportation sector. And so with all of that, they're very interested in looking at direct air capture, and they're willing to pay up to $200 per ton of CO2 captured permanently from the atmosphere. And you don't have to build the direct air capture plant in the state of California, because their philosophy is it doesn't matter where you actually pull the air out or pull the CO2 out. They will offset their footprint from that direct air capture and will be willing to provide that credit. And then finally, these are just a list of some of the construction opportunities. Synthetic aggregates, there's a couple of companies. There's one called OCO and Blue Planet. So these are companies already doing this kind of work today, but it's a matter of doing our best to try and exploit where all the alkalinity is, where all of the best suited CO2 is to get these kinds of reactive products. There's also a company called Carbon Cure that uses less cement in making concrete, for instance, to reduce the footprint. And then in the curing process actually absorbs CO2 throughout the curing. And so with that, I'm going to hand it over to Noah to talk specifically about the project that we're doing at the Pennovation site at the university.
Absolutely. Thank you, Jen. So one of the specific ways in which we operate on that crux between direct air capture and carbon mineralization is the magnesium oxide or MgO looping process. In this process, we start with a magnesium carbonate rock that's sent into a high temperature reactor for a process known as calcination. So when the magnesium carbonate reaches 350 degrees Celsius or above, it breaks down into two component parts, magnesium oxide and CO2. And the magnesium oxide that's produced from this reaction is highly reactive with ambient CO2 at like room temperature and pressure. So that means that we can essentially lay out this rock over land, and throughout the course of a year, it will naturally reform these magnesium carbonates. And after a year, you can recollect this material and send it back to the high temperature reaction step, where you once again produce MgO and CO2. So essentially this can continue cyclically, and after each high temperature reaction step, you have a high purity stream of CO2 that you can either store or otherwise utilize, as Jen mentioned previously in her presentation. You can go to the next. So the first step in our analysis of this process was to determine the economic feasibility. So we performed a techno-economic assessment on this magnesium looping process using already available equipment and infrastructure. And to do this, we did perform two different scenarios, a lower bound scenario with more optimistic parameters to allow for higher process efficiency and lower process cost, and then a more conservative estimate. And we found that this process could cost roughly $40 to $160 per metric ton of CO2 removed from the air, which is important because this indicates that it could be economically competitive with the current leading options for direct air capture, the solid sorbents and liquid solvents that Jen outlined. And while the economic analysis showed that the process can be competitive, there's a lot of important experimental parameters that can contribute to the process efficiency and overall feasibility. For example, the feedstock choice. The techno-economic assessment was carried out for magnesium carbonate to magnesium oxide, but there are other minerals such as calcium carbonate and calcium oxide, as well as the mine tailings that Jen mentioned earlier that could be feasible for this type of a process. And it's important for us to determine how these parameters impact both the reactivity of minerals, the CO2 uptake, and their subsequent impact on the economics of the process. So our first set of experiments was essentially a batch reaction with this magnesium oxide. We set out two 15-centimeter Petri dishes inside of these boxes that you can see here with two industrial CO2 sensors strapped to the lid. And this told us the transient evolution of the concentration of CO2 inside of the reactive box, which told us essentially how fast these minerals were able to take up the CO2 from the box. And then we would lift the lid essentially to replenish the CO2 inside and close it again in a batch form to see how the reaction rate evolved with time. So this is the plot of the experimental results from these cycles. You can see over the first 7 hours, we performed 5 different batches, and each trial showed that the concentration started at roughly 450 parts per million of CO2 inside the box. And within 45 minutes, the box was able to bring, or the mineral was able to uptake enough CO2 to bring the concentration down to about 100 ppm. And it was fairly consistent, which is good. So in order to validate these results in a little bit more robust manner, we set up larger experiments using what's called a Licor soil flux chamber. And what this does is create a seal over the magnesium oxide plot, and it circulates the gas that's in that chamber's headspace. So it gives you the concentration of CO2 over time. And what the instrument reads out is an instantaneous flux of CO2 for the mineral. And we did this for 8 different bed depths, so the amount of MgO that can be stacked on top of it, from 2 millimeters to 9 millimeters. And the results of this experiment are twofold. First, the specific rate of CO2 uptake per gram of material was fairly consistent. And this indicates that up to 9 millimeters, the system's likely not limited by the diffusion of CO2 into the bulk magnesium oxide material. However, what you can see in this image is that the rate drops off. So it starts at roughly 1 e to the -8th, and it drops off fairly rapidly by 3 orders of magnitude. And while we're not yet sure exactly what causes this drop off, our next series of experiments will be trying to bring the rate back up, as well as determining why exactly this drop in CO2 drop in CO2 uptake occurs. In addition to the laboratory scale experiments, we're also setting up larger experiments at the Pennovation Center in Grace Ferry. And this will help determine the impact of multiple experimental parameters on the CO2 uptake, including the bed depth, how high we can stack the magnesium oxide, the feedstock choice. So we'll be evaluating 4 different types of feedstock, including both magnesium and calcium variants, as well as agitation frequency as a way to bring up that CO2 uptake rate, seeing how often we would have to agitate and whether agitation has a great effect on the uptake of CO2 from these minerals. And at the bottom, you can see, that there's almost 2.5 tons of material that we're going to be using to do these plots, and that the plots are 1 meter by 1 meter. So this is a very large increase in scale from what we've been doing in the laboratory with our Petri dishes. And then in addition to working on the CO2 uptake of the process and trying to optimize those process parameters, it's important for us to focus on the feedstock itself and determine what makes a reactive mineral feedstock. So to characterize these materials and their alkaline reactivity, we are working with collaborators here at Penn on the materials characterization itself. Additionally, we're looking at those important experimental parameters and have multiple variations of those to kind of determine the impact of both calcining time and temperature on the reactivity of the magnesium oxide feedstock, as well as some of those more ambient conditions like relative humidity and temperature. And then finally, outside of the magnesium oxide looping work that we've been doing, there are other experiments in the lab that are more broad and working with a broader subset of alkaline feedstocks, including the mine tailings that Jen mentioned earlier. So, question.
Okay, I think, yeah. So we're happy to answer any questions.
All right, that was great, terrific. Thanks very much. Can you guys hear me, see me?
Ken, and
okay.
Mark, would you like me to leave this up? This is more resources if people are interested.
Yeah, I think that'd be great. So OSIC gave me one task that I'm gonna I'm gonna turn my assignment in just a little bit late and hope that it's still okay. I just wanted to note, although 3 of you have already found for yourselves, that the Q&A button is open and active, and if you log your questions in there, I will kind of work my way through them. So sorry about that, Osik, and glad you guys are already asking. Noah, I just had one quick question. How much of that agitation are you personally responsible for?
So we're trying to automate it. Hopefully we'll have a motor. It's going to be like our auger that you use to plant bulbs in a garden. And hopefully we'll be able to automate it with a motor so we can have it on an incremental schedule. I'm hoping that I will not be responsible for daily agitation, but we'll see how the automation goes.
Yeah. But until then, you are, right?
Yeah.
That is what you're doing.
The lab experiments, it's by hand.
But there's a little longer answer to that too. Do you want to say something about Copperstone?
Yeah, absolutely. So we're working with a robotics company that's out of Canada, and they're working on autonomous stirring robots. They work primarily with mine tailings and trying to agitate pond tailings. So it's essentially a slurry that they keep their waste in. And they're working with us and the magnesium oxide material to figure out what type of robot geometry essentially would be best for the tailings and this powder-like material that we're working with.
Interesting. Well, okay, Noah, if you don't mind, I'm gonna stick with you for a minute because a couple of the questions that have come up are kind of directed towards your presentation. I'll read this for the benefit of everybody. I think I'm gonna go with the chemical abbreviations though. So in MGO looping, you manufacture CO2 only to end up absorbing some CO2 from the atmosphere. Is there a net positive CO2 removed, or are equal amounts of CO2 removed and manufactured?
So that's a really good question because the life cycle accounting of CO2 for these processes is a very important point. In this process, you do produce a pure stream of CO2. So it ultimately depends on what you choose to do with that CO2, whether or not the process will result in net negative emissions. So if you choose to utilize that CO2 in fuel, like Jen mentioned, then you're re-emitting it back into the atmosphere. However, if you put it into geologic storage, you have the opportunity to remove CO2. Now, it also goes to say that you have to consider the energy resource that you're using to power the calcination and the electricity requirements for the system, as well as the physical footprint, like the CO2 footprint of manufacturing a calcination facility for the process. So if you are sequestering CO2, we have calculated that it should result in net negative emissions using natural gas, both electricity and for the calcination process. One caveat to that is that the calciner that we've done this for is an oxy-fired calciner, which means that it's fed with nearly pure oxygen for the combustion environment, which means we can co-capture the combustion emissions from natural gas with the emission or with the captured CO2 from the atmosphere, which allows us to offset what would otherwise be combustion emissions from the process.
And I can't help but do a little plug here myself. Maybe we talk about our collaborators. So we have a collaborator in Australia that's actually designed an electric kiln that we're working with. And the name of their company is called Calyx. And there's not a lot of these types of things out there, not a lot of electric heating to the temperatures that are often needed for calcining. So Calyx is one. And then it was just recently made aware to me last week that BASF also has about 1,000 degrees C electric heating unit as well. But this is really important. This is a really important piece because, you know, we might think about, you know, a lot of, when you use natural gas, it's decarbonization. But, you know, there is a community that says, hey, you know, can we stop doing that? Can we stop using natural gas? And isn't carbon capture just an enabling, you know, the use of fossil fuels? And so if there's an alternative to use electric and you have green electrons available, and those green electrons wouldn't be better used to displace a coal-fired or natural gas-fired power plant nearby, then absolutely using an electric calciner for this process would be really the best way. And then you're defossilizing the whole process. And then you're maximizing the carbon removal from the atmosphere when it's coupled to dedicated geologic storage.
Now, what I particularly liked as moderator of Jen's answer there is it anticipated a later question, Thomas's question about, you know, for how do you all foresee a role, a growing role perhaps for renewable energy, which, you know, broadly defined includes exactly the strategy that you just outlined there, Jen. That's good. So I have one more kind of more technical question that's come up here from Nancy. Could you explain more your future work action related to CO2 uptake on its effect on RH, is that relative humidity, and temperature?
Yeah, absolutely. So we've, in our preliminary trials, have seen that the carbonation rate depends, or could depend fairly heavily on the relative humidity and the available water in the air. This is somewhat intuitive since the mineral is hydrated initially from that water in the air. So we would like to test more controlled conditions. So we've been doing it ambiently, which means that the relative humidity and the temperature changes daily, hourly, so on different intervals. And that is great for the original, like the initial data, but we would like to be able to map how that is affected by both the relative humidity and the temperature. They both should be important parameters that affect how fast these minerals can take up CO2. So we're just going to incrementally change the relative humidity and the temperature between allowable bounds that you see ambiently. Roughly probably 10% to 90% relative humidity, and then temperatures between freezing and probably 100 degrees Fahrenheit, depending on what resources we have available.
Thanks. Thanks. Okay, so I'm going to combine a couple of the kind of policy-oriented questions, one from Corey and one from Samuel here. I'll read Samuel's first. This technology can be made price competitive with other carbon capture methods, but can it be made price competitive with not putting the carbon in the air in the first place? And if so, how? And if not, what does that imply? I have a few answers myself to that one, but I'd love to hear what you guys have to say. And then Corey has also asked, kind of beyond, I think, Jen, the context in which you place the Petra Nova closing, what does the shuttering of the plant mean about the future of CCS kind of more generally? What kind of pathway does it imply?
Can I answer the second one first? And then oh boy, I might run the risk of forgetting the first, but that's okay. Maybe.
What I'm here for.
Okay, good. Well, that second one is interesting. So, you know, and I'll just reiterate what I said before, and that is, you know, the closing of Petra Nova wasn't associated with carbon capture not working. There's been some kind of mismessaging of that. A couple of reports out there saying, you know, the carbon capture rates were pretty low. Well, those numbers and those reports were actually cherry picked, because in the early stages of the project, there was a period where they actually shut the plant down. And so in the recent reports that claim that the reason why Petra Nova shut down was because the carbon capture process wasn't effective, it just wasn't the whole set of data. It was just over a 6-month period where the plant purposely shut down. And so that's unfortunate that got out into the community and then kind of mismessaged and undermined really the role of carbon capture. But the second thing I'll say is this also goes to the policy. So 45Q is a federal tax credit that was developed to incentivize carbon capture for enhanced oil recovery in particular, and maxes out for that at $35 a ton. But that number was helpful, but the real reason why carbon capture in that case was coupled to EOR is because when you do the carbon capture, the enhanced oil recovery process allows you to produce oil, and then that oil has a value. And the carbon capture is expensive, you know, by comparison. So for instance, I'll mention for enhanced oil recovery today, the operators get 80% of the CO2 naturally from the earth. And many of the operators actually own the mineral rights to the natural formations of CO2. The entire utilization industry for EOR in the US is 72 million tons of CO2 per year. The total utilization industry, which includes food and beverage uses of CO2, decaffeination, all that, 80 million tons. So it's like 8 million tons utilization of CO2 is everything outside of EOR. So EOR utilization for CO2 is a big, big deal, but most of it's naturally sourced. And it can be as low as, you know, cost the operators $10 a ton if they own the mineral rights, maybe up to $40 a ton if they're getting it from an anthropogenic source. And so carbon capture from coal is an anthropogenic source. And so it's on the higher end. So now if the price of oil drops, that's not, that project in sourcing CO2 is not going to be effective. They're going to find the CO2 somewhere else. And that's why it shut down. And that's why something like 45Q would be better served if they could actually have a bigger gap between EOR and dedicated storage, such that when we have projects associated with carbon capture, they're not crippled by being connected to EOR. That cripples the technology, in my opinion, in terms of deployment, because it's like, okay, the price of oil drops. Now all of a sudden it's not economic anymore. But it's if we just do it to dedicated geologic storage, I think we would be a lot better off. And I think that there's work in doing that and changing 45Q and actually creating a bigger gap and not just the $50 to $35.
Yeah, that's great. That's actually that's a great question and great answers. One of the things that I wanted to ask you more about was along those very lines. I mean, is your basic instinct around the policy pathway for greater uptake in carbon capture along the utilization path or along the storage path more generally? I know you just applied storage with your smart fix on 45Q, but how about just more broadly? Because we can think about a bunch of different possible policy instruments.
Sure. Yeah.
Would you invest the next effort on, say, some kind of tax revenue through a credit or through a tax on storage generally?
I mean, I think it would be great. There's just red tape associated with storage. It's not that that's actually the expensive part. So when you look at, and we're not talking about direct air capture, when you look at point source capture from a natural gas fired power plant, it's about $60 or $70 a ton. The cost of putting it underground, like drilling a well and injecting it, is about $10 a ton. So it's not that it's expensive that we don't actually do it. It's because you've got to actually get an EPA certified Class 6 well. The neighbors have to be okay with it. You know, you're putting CO2 in the earth. Of course, we store natural gas today, and that's actually a lot worse than CO2. And in Texas, the neighbors are okay with putting CO2 in the earth because they've been doing it since 1972. And with enhanced oil recovery since 1972, you only need a Class 2 well. And so it's like the green light is there to do it today. And those formations are pretty safe bets because they've been storing oil and gas for millions of years. And so it's unfortunately probably gonna be the bridge for some time, but I think there needs to be a lot more effort in terms of education and broader communication of what it means and what it means to store CO2 in porous media deep in the earth so that people become more comfortable with the concept. There's like the Central Valley of California has great sedimentary basin formations for doing this. But, you know, there's a lot of pushback in terms of putting CO2 in the earth. And so my view is like, yes, we need to do that, but we also need to make sure we have the public communication and the acceptance and understand the environmental justice issues associated with it, and really doing all of that important work. And I think that's where probably the cost and the time comes in, right? Not the actual technology. The technology itself is not expensive. The other part, I'll just say this, it's twofold. The other kind of utilization, so that's dedicated storage, and I'm all for it, and like figuring out more how to get people to understand what it all means. But the other piece is, it's not just utilization, doesn't just mean enhanced oil recovery. Another way to think about utilization is think about the products that we're all so dependent on in the sectors that are really hard to avoid. We all like our cars, and not all of us are privileged to be able to, especially if you're in a dorm or you're in an apartment, where are you going to charge your car? If you want an electric car, your moral fabric may want that electric car, but like logistically, you just can't make it work. And so there's going to be, we have an investment in transportation associated with liquid fuels today. And it's not just our own, passenger cars, but it's also aviation, and so that's in the other sector that's going to be hard to avoid is we use plastics. It's very convenient. We wear clothes that are made out of crude oil, textiles, nylon, polyester, all these products that we use every day. And it turns out that we can remove our dependence on crude oil for making those products. And it's just chemical engineering. It's really as simple as that, because you can use CO2 as a feedstock. It can be CO2 from air even. And then you're thinking circular. It's not negative. It's going to go back into the atmosphere when the product is used, or maybe even disposed of, or eventually oxidized. And then you have to think about where you're going to get the hydrogen from. And there's lots of options, but today really, is green hydrogen. But it's expensive today because the electrolysis units are very capital intensive in terms of cost. And so this is something like that. We just need to figure out we need more investments to get the cost of electrolysis down, so that we can get more green hydrogen to react with CO2 to actually do the circular economy concept, so that we don't have to rely on crude oil for the products that we want to use every day.
That's terrific. Osik, did you turn your video back on to remind me of the second thing I forgot, which is that it's about time to start moving to closing comments?
I think we have one more. We have some time for another question.
Great. Okay, I've got a follow-up from Samuel. The only one I'm seeing. Well, I guess there's one here that I have to say I don't understand, so I'm just going to read it, and maybe it'll make sense to chemical engineers. What is the type? Whoops! No, it's gone. It just disappeared.
Oh no!
You magically answered it, I believe. Okay, that's fine. And then there's another question here, kind of a follow-up from Sam about. I think I understand this one about. Is there a known cost per ton of not burning the carbon?
Oh yeah, that's right.
Right. Does anybody want to say anything about that?
I mean, I would just say those are all the traditional things that we have the skill sets to do all of these things. We're just not doing them fast enough. And yes, they are cheaper. Carbon capture from point sources, but that's not all. There's, the costs of solar have come down significantly, but it's regional. Where there's good opportunities for that. Wind is very regional, but boy, in Oklahoma and Texas, it's cheap. So it's like all these things, but it's a portfolio, and it's like, they're very regional portfolio. And that's why it's been so difficult, is because there's no silver bullet. There's no easy fix. And in order to things to be, socially and environmentally equal all around, it means getting on the ground and understanding the stakeholder issues regionally, making sure jobs are not going to be lost, making sure that places aren't going to be more polluted. And that does take time, and that does take cost in terms of adding to each one of these solutions. But it will always be cheaper to just avoid the emissions in the first place. And the carbon removal, even NOAA's SLIC concept, is more expensive than just simply avoiding the carbon.
Yeah. And one of the things, I add briefly that we've also gotten, as Jen consistently is referring to, the need for that portfolio of technologies in order to adequately address, at this point, simply the sheer volume of the problem. So too has policy grown a little bit more sophisticated, right? 10 years ago, we might have said, hey, the answer is a carbon tax that approximates the social cost of carbon, which, you know, is somewhere far north of $50 a ton. You know, there are some carbon taxes in some parts of the world that are routinely $100, $150, $200 a ton that, you know, is much closer approximation to the fully accounted social cost of each of those tons of emission. But we've also come to understand that the tax alone is probably going to be insufficient, especially at any kind of politically feasible rate. And then we have to wrap around that tax a set of regulatory requirements that actually come with mandates about reductions. And some of the, because so much of what this talk has been about forms of waste. I think that there's lots of well understood kind of policy instruments that allow us to kind of treat this waste as value and monetize it either through policy or, when possible, through some kind of product like utilization in the real marketplace. So it's all great, great stuff. And Thomas has thrown in some other questions, but I don't think we have time to address those anymore, do we, Osik?
I think we're, you know, you guys have previous other engagements, and I don't want to keep you so that you make your next appointments. But it's a fantastic conversation, and of course, Professor Wilcox is available. If you send us information or if you need her information, we can pass that on to you. Noah is also available, so if you want to ask them, communicate with them directly, that'd be perfect. They will give you a more detailed answer, as well as, you know, Mark is also available if you want to address additional questions to him. So with that, I want to thank Professor Wilcox, Noah, and Professor Hughes for this fantastic session about how we can actually remove carbon from the air. It's a very interesting, complex scientific process, obviously, as we heard through the presentation, but it's, of course, doable. And like Professor Wilcox says, the best thing to do is not to put the carbon in the air to begin with. So let's all strive for that. In closing, I'd like to acknowledge a few people that have made these panels and speakers possible here at Penn Engineering all week long. I want to recognize our colleagues at SETS, Andy Perch and Paul Schaefer, our communication team at Penn Engineering, John Gorky, Ivan Lenar, and Olivia McMahon. I'd like to also acknowledge the Penn Engineering Green Team, Leandra Davis-Kern, Diane Penatris. Diane is here with us all the time. She's behind that Penn Engineering logo you see there. That's Diane, and she's been just priceless this week, helping us with all the technical things and putting this together. I'd like to also thank Lily Hoot and James Sklar-Vonas. I want to also thank the Dean's Office, Shambra Jones, and also Sonia Guag, Ross Composto, and all of our panelists this week. And of course, last but not the least, I'd like to thank our leadership, our Dean, Vijay Kumar, who always says fondly to our students, you have to invent the future. And with climate, we need inventions of the future that will help us solve this problem. And one of the things, as Professor Hughes said earlier, that is a common thread of all the panels in this week's program. The one common thread that runs through it is collaboration. So we've had folks from the Weizmann School of Design. We have people from the Kleinman Energy. We have people from Perry Waldhouse. We have people from ECA, African Development Bank. And throughout all these sectors, we have solutions or ideas of how we can begin to combat climate change and its consequences. And so with that, I thank you all. Have a great weekend. And lastly, please stay safe from COVID. Thank you from all of us here at Penn Engineering.